This is the fourth lecture in general chemistry. In this lecture, we're going to be talking about Lewis structures and molecular shapes, and this information can be found in Chapter 10. This is the first lecture after the first exam, so I wanted to bring this slide up again just to remind us what part of the class we're in. Chapter 7, 8, and 9 were covered on the first exam. Now we're moving on to Chapter 10, which builds off of the information we've gone over in the first three chapters. This lecture, Chapter 10, and next lecture, Chapter 11, will be all building off of the first exam material, and then we're going to have a disconnect. We're going to go backwards into Chapter 4. Okay, 10.1 covers Lewis structures. I wanted to bring this slide, we saw this slide last lecture, but I just wanted to bring it up again. Lewis theory, the bonding theory, and this says where the idea of the octet comes from, where a set of 8 electrons in a valence shell is a filled shell. And again, there's some rules to this, like hydrogen and all elements left of carbon don't require a full octet. And Lewis symbols, we've seen these before. This is where you have the valence electron shown as unpaired dots, and the number of unpaired dots equals the bonding capacity of that element. But we're going to move on from Lewis symbols to Lewis structures. So just like in Lewis symbols, electrons are represented as dots. A shared pair of electrons represents a covalent bond. So you can show the covalent bond between two hydrogen as 2 dots between those hydrogen atoms. But more commonly, this is shown when there are shared electrons forming a bond. We show it as a line between the 2 atoms. So a single bond, 2 atoms sharing 1 pair of electrons. A lone pair is unshared pair of electrons, and it's associated with just 1 atom. And you can also talk about a bonding pair of electrons, and that's a pair of electrons shared between 2 atoms to form a covalent bond. For nonmetals, the shared electrons, they share electrons in their covalent bonds to achieve noble gas electron configuration, or also known as a filled shell. So for hydrogen, each hydrogen has 1 valence electron. When they come together and form a bond, now they're sharing the 2 electrons, the 2 valence electrons that they started with, and their shell is filled. When we look at water, oxygen and 2 hydrogen atoms, oxygen has 6 valence electrons, hydrogen has 1 each. They come together, they form 2 bonds, and with that, the hydrogen fill their 1s shell, and the oxygen now has 8 electrons surrounding it, 2 non-bonding pair, and 2 bonding pair, so its octet is now filled. The steps in converting a molecular formula into a Lewis structure, the book gives a number of steps. So it's good when you're first starting to do these to try to follow these steps. If you have some experience, say from high school chemistry, and you're comfortable with Lewis structures, you might not really need to follow these steps exactly, but if you're just starting out or you're uncomfortable at all with Lewis structures, I would suggest that you try to follow these steps as closely as you can. The first step is to start with a molecular formula. and you place the atom with the lowest electronegativity in the center. And all the other atoms that have higher electronegativities then go around the outside of that center atom. The second step, you sum the valence electrons. Now, I usually do this step before I do step 1. You can do step 1 or step 2. It doesn't matter the order of these first 2 steps. And also, it's important to note to be aware of the molecular charge. If there's a negative charge, you have to add electrons. If there's a positive charge, you have to take electrons away when you're summing the valence electrons. And we're going to see examples of that later on. So the third step, you draw single bonds between the center atom and the atoms on the outside of the center atom. And each time you draw a single bond, you subtract 2 electrons. And step 4, you give each atom 8 electrons, a full octet, or in the case of hydrogen, 2 electrons. And this should lead you to the Lewis structure. So let's see an example of NF3. So the molecular formula, we have it's NF3. Now, when we're trying to place these atoms, which atom in this molecule has a lower electronegativity? That would be nitrogen. So nitrogen will go in the center. Another way you can tell is because there's only one nitrogen atom and there's 3 fluorine atoms. So it wouldn't really make sense to have one of the fluorines in the center and the other 2 on the outside. Okay, so there's our atom placement. Now we need to sum up the valence electrons. And you see that there's 1 nitrogen. Nitrogen has 5 valence electrons. There's 3 fluorine. Fluorine has 7 valence electrons. So we get a total of 26 valence electrons. And the next step, we need to draw single bonds between the center atom and the 3 outlying atoms. There we go. So we've used 6 electrons in those bonds out of our 26. So we're going to have 20 electrons remaining. Now the first thing to do would be to fill the octet of the surrounding atoms, the surrounding fluorine atoms. So we give those all, I guess I'll show this as an individual step. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we use 18 of the 20 remaining electrons to fill the valence shell of fluorine. So each fluorine has 6 non-bonding electrons plus 2 electrons that it's shared in bonding. So each fluorine has 8 electrons associated with it. But we still have 2 electrons remaining from our total 26 electrons. So where do those go? Those go on the center nitrogen. There you have the final structure. And you'll notice too that nitrogen now has a full octet. It has 6 electrons associated with it that are in bonds, 3 bonds, and it has 2 electrons that are a non-bonding pair, so it has a full octet. And this is the final Lewis structure for NF3. So just to reinforce this, the steps to use. So number 1, this is a little bit different than your book, but I would say determine the valence electrons first. So you sum the valence electrons for all atoms in the molecule, and you have to add or subtract electrons to account for the molecular charge. And then arrange the atoms in a pattern to show how they're bonded. And the atom with the largest bonding capacity will be in the center, or another way to put that, it would be the atom with the lowest electronegativity. And H hydrogen atoms are always going to be on the outside. And I think that looking at it in terms of bonding capacity is really the appropriate way to do that. Thinking about electronegativity, that rule doesn't always work. So try to stick with looking at bonding capacity, putting the atom with the highest bonding capacity in the center. And again, hydrogen only has a bonding capacity of 1. It is always going to be on the periphery. And then finally, the final part of step 2 would be connect the atoms with single bonds. Okay, then you complete valence shells by adding lone pairs to the atoms connected to the central atom. And you match the number of electrons in the structure to the number of valence electrons calculated in step 1. And if all of your electrons are used, you're done. If not, any remaining electrons you place around the central atom. And you complete octet around the central atom by converting lone pairs on adjacent atoms to bonding pairs. If, for example, you do all 4 of these steps and your center atom still does not have a complete octet, then you would take a lone pair of electrons on an adjacent atom and form another bond, a double bond, or a triple bond if needed, until you fill that octet on the central atom. Okay, so this is a example double bond. It's 2 electron pairs shared by 2 atoms, and that you represent this as a double line. A classic example of a molecule that has a double bond would be O2, and oxygen tends to form double bonds. So we see the Lewis structure for O2 is what's shown here on the right. It's 2 oxygen atoms with a double bond, and they each have 2 lone pairs. A triple bond would be 3 electron pairs shared by 2 atoms, and you show this as a triple line. Classic example of that would be N2, nitrogen gas, on the Lewis structure shown here. You notice that each nitrogen has a full octet. They have 6 bonding electrons and 2 non-bonding electrons associated with them. Okay, let's look at O2 and N2. Let's try to work through these. So for the valence for O2, we have each oxygen has 6 electrons. There's 2. So we're going to have a total of 12 valence electrons. Now we arrange the atoms, and this is, pretty simple because there's only 2 atoms in this molecule. And we draw a single bond to start with. That takes 2, so we have 10 electrons left. The next step, we're going to complete the valence shell. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 non-bonding electrons and 1 bonding pair to give us our 12 valence electrons. But you notice that the octet for the oxygen on the right is not complete. So we're going to need to take 2 of the non-bonding pairs, 2 of the non-bonding electrons off of the oxygen on the left and make a double bond. So there we have the final Lewis structure. The octet is complete on each oxygen atom, and we've used the total of 12 electrons. Now for nitrogen, each nitrogen has 5, so we're going to have a total of 10 electrons to use. The bonding pattern is the same. There's 2 atoms. So we've used 2 in that single bond, 2 electrons, so we're left with 8 more. So if we try to fill the remaining 8, we would get 1, 2, 3, 4, 5, 6, 7, 8. And you notice now each nitrogen only has a total of 6 electrons associated with it. 4 non-bonding electrons and 2 bonding electrons. So we're going to have to complete the octet, and we do that by taking away non-bonding electrons. So let's try taking away 2 non-bonding electrons first and see. So if we had a double bond, now one nitrogen, the nitrogen on the right has a full octet, but the oxygen on the left, the nitrogen on the left still does not have a full octet. So we need to do this step again. So we remove a non-bonding pair on the right nitrogen and form a triple bond now. And now we're left with a molecule that has both nitrogens, full octet, and we're using a total of 10 electrons. All right, try this practice question. Same steps, but try Lewis structures of H2O, which is water, H2CO, and CH4, which is methane. Right. Okay, let's start with water, H2O. Each hydrogen has 1 valence electron, oxygen has 6, so we have a total of 8 valence electrons. We arrange the atoms. Oxygen has the highest binding capacity, so it goes in the center. We draw single bonds, so we've used 4 electrons in the bonds. So complete the hydrogen on the outside, their octet, or duet rather, is complete. So they're happy. Now we just have to satisfy the octet on the oxygen. So we've used 4 electrons in bonds. We have 4 left, so we put the 4 around the oxygen. And that is all we have to do with water. We skip step 4. The valence on the hydrogen were complete because it's hydrogen. We didn't have to add any non-bonding pairs to them, so we could skip down to step 5 really and complete our octet on the center atom with our remaining valence electrons. Now let's do H2CO. The valence electrons would be 1 from each hydrogen, plus 4 from carbon, plus 6 from oxygen. That'll give us a total of 12. Now we have to arrange the atoms. How do we do that? Well, which has the highest binding capacity? That would be carbon. So carbon will go in the center. And then if we place the hydrogen and the oxygen around it symmetrically, we'll get something like this. Then we add single. We add the bonds around the center atom. Then we try to fill in the valence shell on the outside atoms with our remaining valence electrons. So we've used 6 electrons, we have 6 remaining. 1, 2, 3, 4, 5, 6. So in this structure, oxygen would be full octet, hydrogens are fine, but the center atom, carbon, is not. It's not okay. It does not have a full octet. So we're going to have to remove a set of those lone pair on oxygen and make a double bond. To fulfill the octet on the carbon. So this would be the final Lewis structure for H2CO. Now finally, on to methane, CH4. We're going to have 4 electrons from 4 hydrogens and 4 electrons from carbon. That gives us a total of 8 valence electrons. Carbon goes in the center. It has the highest binding capacity. And we'll draw in the bonds to the center atom. And we've had four bonds. We've used 8 electrons. The valence on carbon is complete. The octet on carbon is complete. Hydrogen is good. So we're done with this Lewis structure. This one is pretty simple. Okay. Practice question 2. Draw the best structure of cyanide, best Lewis structure of cyanide. And the hint here, carbon is the center atom. Remember, it has the highest binding capacity. So what is true about the structure of cyanide? If you remember the steps, we need to first calculate the number of electrons we have. We have 1 from hydrogen, 4 from carbon, 5 from nitrogen, total of 10. We put the atom with the highest binding capacity in the center, the other 2 around it. We start with single bonds. So we've used 4 electrons in bonds. We have 6 remaining. 1, 2, 3, 4, 5, 6 around the outside atom. And this is incorrect because carbon, again, doesn't have a full octet. So we'll add a double bond now. Take 2 of those non-bonding electrons and make a bond. This still isn't good because now carbon only has 6 electrons associated with it, or 3 bonds. So we have to do this step again and make a triple bond. So this is now the Lewis structure, the correct Lewis structure for cyanide. And now let's look at our choices. So what do we have? We have 1 non-bonding pair on nitrogen. So that would be B, would be the correct answer. A term I want to bring up now is allotropes. And a good example of allotropes is oxygen and ozone. So this is different molecular forms of an element. So the element is oxygen, and the different forms would be ozone and oxygen, molecular oxygen. Another example is with carbon. I think everyone has heard that graphite and diamond are both carbon. They have different molecular forms though, which is why they have different properties. And your book gives this figure about the formation of ozone, which becomes important when you're talking about the ozone layer. and atmospheric chemistry. The formation, we're not really going to be concerned with that formation, though, in this class. What we do want to look at ozone for is something that's known as resonance structures. So when we draw the Lewis structure for ozone, we see that we can have two equivalent structures for the molecule ozone, and those are shown over here on the right, where you have one double bond and one single bond between three oxygen atoms. And you can put that double bond on the left side of the molecule or the right side of the molecule. So which one is correct? Does it spend some of its time in the structure on the left side and some of this time on the structure on the right side? And the answer is it's really an average between these two. And your book gives the analogy of a blue horse and a red donkey. Is it converting between a blue horse and a red donkey? And the answer is no, not really. It's really kind of a mix of the two, which would be a purple mule. And the evidence we have for this, that it is a mix, when we do find the crystal structure from ozone, we see that the bond lengths are both 128 picometers. It's not like one side has a longer bond and the other side has a shorter bond and they flip between being long and short. They really are the same length. So it is an average of these structures. And a better way to show this is shown down here with a dashed line on both sides. So a single bond would be longer than a double bond. But in ozone, the bonds are equal. So that means they really both are a mix between single and double bonds. And this dashed line way of showing electrons is called electron delocalization. So Lewis structures depict electrons as localized, either on an individual atom as lone pairs or in a bond between two atoms as a shared bonding pair. In a resonance hybrid structure, electrons are delocalized, and that is showing them being spread over a few adjacent atoms. So this dotted line indicates that those two electrons are being spread between all three oxygen atoms. And this gives us fractional bond orders. We talked a little bit last time about bond order. And resonance hybrid structures will give you fractional bond orders. So let's calculate the bond order for ozone. So you have 3 electron pairs in ozone, and you have 2 bonded atom pairs. So that will give you a bond order of 1.5. Another way you could think of that is six electrons total, 1, 2, 3, 4, 5, 6, shared between 3 atoms, which would be that would be 2. So you'd have 2 bonds, and now 2 bonds shared between 3 atoms. So that's really not a very good way of thinking about it. These fractional bond orders, it's really hard to to calculate them sometimes. It's best, at least in my head, to think about it. You have 3 bonds, 3 single bonds, and you're spreading those out between two bonding sites. So really, you have 1 extra bond that is changing. So it's half the time on one side, half the time on the other. That's where you get an extra half bond order. Now, if we look at examples of resonance, there's many different examples in organic chemistry, and you're not going to need to know these for this class, but when you go onto organic chemistry, you're going to see examples, many examples of resonance. And in biochemistry, these 2 molecules at the bottom, the peptide bond especially, that's really big in biochemistry. And there's resonance. You see there's a double bond between carbon and oxygen that can switch to a double bond between the carbon and the nitrogen in a peptide bond. So let's practice resonance structure. Draw all possible resonance structures for SO3. And what is the SO bond order? So let's first draw the Lewis structure. Sulfur now would be the center atom, and they have equal bonding capacity, but center sulfur, is less electronegative, so it will now go in the center. And another hint with that would be that there's only 1 sulfur and there's 3 oxygen. So put that sulfur in the center. Now we place the oxygen around the outside of sulfur. How many valence electrons do we have? Well, they each have 6 valence electrons. And there are 4 atoms, so that will give us 24 valence electrons to work with. If we draw single bonds, that's 6. We've used a total of 6 valence electrons. Now we have 18 more to use. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are all the electrons. Now, what's the problem with this structure? It's that sulfur doesn't have a complete octet. So we're going to have to take 1 non-bonding pair and make a double bond. So we'll show the double bond up top first. I'm not going to draw in all the valence electrons, but just know, the non-bonding electrons on the oxygen atoms, but just remember that they're there. So this is the complete Lewis structure for SO3. But the problem with this is that you can show that double bond in other places, and it would be equally correct. So really, to indicate that these are all 3 equivalent structures, we need to draw brackets around each of them and then show that they're equivalent by adding double-headed arrows. And that would be the correct way to show the resonance structures for a molecule. Another way you could show this would be with the dashed lines to show the delocalization over the entire molecule. Now, what about the bond order? Let's try to explain this a little bit better than I did a couple slides ago. We have single bonds between the sulfur and all three oxygens, but we have one double bond that is being shared between the three. So we have a bond order of 1 plus there is one double bond being shared between 3 bonds. So that would give us a bond order of 1 1/3. Now as Lewis structures get more complex, there becomes times when you can draw different structures for the same set of atoms in a molecule. And they all seem to follow the octet rule. But how do you decide which structure is more correct? And that would be by using what's called formal charges. So the formal charge is a measure of the number of electrons formally assigned to an atom in a molecule. And how you calculate the formal charge is you first take the number of valence electrons in an atom, and then you subtract the quantity of the number of non-bonding electrons in the structure, in the atom, how the structure is drawn, plus 1/2 of the number of bonding electrons in that drawn structure. And down below you see a table, and this is the calculation of formal charge for the resonance structures of N2O. So how do you choose the best structure, or the most stable, for instance, a resonance structure? Well, formal charges equal to 0 or close to 0 are the most stable. And when you have a negative formal charge, that negative formal charge needs to be on the more electronegative element in the molecule. So if we think back to the table, trying to select the best resonance structure, the best structure would be the first one. And why is that? Well, when we calculate the formal charge for the elements in this structure, nitrogen has 0. The center nitrogen would have a +1 formal charge, and the oxygen would have a -1 formal charge. And why is that better? It's better than the structure on the far right because in this structure we have a -2 and a +1 and a +1. So remember that formal charges at 0 or close to 0 are more stable. So a -2 +1 +1 would not be more stable than 0 +1 -1. So we can eliminate that structure. And the structure in the center, let's look at this. Oxygen has 0 formal charge. Center nitrogen has a +1. The nitrogen on the left has a -1. But remember, if we have negative formal charges, it's more stable when they're on the more electronegative atom in the molecule. And oxygen would be the more electronegative compared to nitrogen. So it's really more correct to show a structure where oxygen has a negative formal charge and nitrogen has a neutral or a positive formal charge. So let's practice this. Let's determine the most stable structure for phosphite ion by calculating the formal charge for the atoms in each ion. So phosphite, if you don't know, is phosphorus with 3 oxygens. And when you do the Lewis structure for this, you should come up with two possible structures. One with single bonds to the center phosphorus atom, and one structure with one double bond. Now, if we calculate the formal charges on this, I should mention here, if you didn't come up with this structure on this side, that's okay. It has an expanded valence, and we haven't really talked about expanded valence yet. But try calculating the formal charges on these two structures, and you'll see hopefully which one is more correct. Now, the formal charge is equal to the number of valence electrons minus the sum of the number of non-bonding electrons plus 1/2 the number of bonding electrons. If we look at this structure on the left, oxygens, they're all three the same. So the formal charge on oxygen would be 6, that's the number of valence electrons oxygen has, minus the quantity 6, that's the number of non-bonding, plus 1/2 of 2, number of bonding. And what does that equal? 6 minus 6 plus 1. That would be a formal charge of -1. So all three oxygens have a formal charge of -1. The way I like to think of formal charge, I don't usually remember this equation. The way I think of it is you assign the non-bonding electrons to that atom, so that would be 6, and then you cut the bond in half, so that would be 7 total electrons for that oxygen atom. Oxygen in the periodic table has 6 valence electrons, so there's 1 extra, so there'll be a -1 charge on that oxygen. That's how I normally think of it, but it would probably be better for you to stick to the equation, at least to start with. Let's do phosphorus now. Phosphorus normally has 5 valence electrons. Here we have 2 non-bonding, and there are 6 bonding electrons. So 2 plus 3 is 5. 5 minus 5 would be 0. So in that structure, phosphorus has a 0 formal charge. And you'll notice too, the formal charges add up to the total charge on the molecule. So oxygens are all 3 minus 1, phosphorus is 0, that's a total of -3, and that is the charge on our ion. Now let's look at this structure on the right. These oxygens are both -1. The oxygen, when oxygen has a double bond and 2 lone pairs, that's going to be a formal charge of 0. And now phosphorus has a total of 4 bonds, so its formal charge is going to be -1. And that's 5 minus the quantity of 2 plus 1/2 of 8. So that'd be 5 minus 6, and we're going to get minus 1 for that phosphorus. So which of these structures is more accurate? And that would be the structure on the left. Why is that? That is because the structure on the right, phosphorus has a formal charge of minus 1. Phosphorus is less electronegative than oxygen, so it's much more stable to have a negative formal charge on a more electronegative element, such as oxygen. All right. Now we foreshadowed this a little bit with the phosphite ion. There are actually exceptions to the octet rule. And we talked a little bit previously, molecules that have fewer than 8 electrons, atoms that have fewer than 8 electrons. And that's an example would be anything left of carbon on the periodic table. So a molecule like BF3, we say is electron deficient. So boron doesn't necessarily have to have a filled octet. Its binding capacity is 3. So it needs 6 electrons to fill its shell. Another example of an exception to the octet rule would be a molecule that has an odd number of electrons. And we call these free radicals. A classic example of that is nitrous oxide. Any molecule that has NO in it has a good chance of being odd number of electrons. And the final example, which phosphite was an example of, would be a molecule that has more than an octet. An example we give here would be sulfur hexafluoride. And this is where the sulfur actually has an expanded valence shell. So if we look at nitric oxide, the number of valence electrons would be 5 plus 6, 5 from nitrogen, 6 plus from oxygen, which would be 11 total. So that's an odd number. So what would the formal charges be? Well, if we draw the structure, so if we assign a full octet to oxygen and only the remaining 3 valence electrons to nitrogen, our formal charges would be 0 on nitrogen. We have 5 valence, 3 non-bonding, plus 2 in the bond. So I suppose a more accurate way would be to include a double bond there. Now if we look at oxygen, 6 valence, 4 non-bonding, plus 1/2 of 4 or 2, and we can get the structure to have formal charges of 0 on both atoms in this molecule. The only problem really is that nitrogen doesn't have a full octet, but we don't have enough electrons to give nitrogen a full octet. So the structure is really reasonable, except again for our lack of an octet on nitrogen atom. And these are known, molecules like this are known as free radicals. And why is that? Because they have one unpaired electron. So one of the non-bonding electrons is unpaired. And these tend to be very reactive molecules. An example of one of these molecules is shown over here, where we have one unpaired electron on this nitrogen-oxygen moiety in the molecule. And this molecule is used a lot in electron paramagnetic resonance. In EPR, you measure the change in energy between this spin state of the electron. The electron can be plus 1/2 or minus 1/2, and you can actually, just like other forms of spectroscopy, you can change the energy level. In this case, the electron spin energy level. You can change it from a plus 1/2 to a minus 1/2 and see the absorbance of energy. Again, this is just an FYI for you. You're not going to need to know this in this class. Just presenting this as an example of what free radicals can be used for in science. More commonly, what we're going to see as an exception to the octet rule is expanded valence shells. And this can occur in elements with Z greater than 12. So an atomic number greater than 12, and that occurs starting in the third row. And these elements can expand valence shell by using empty d orbitals. Now, if you remember quantum numbers, when n equals 3, L can be 0, 1, or 2. So it can have an s, a p, or d orbitals. And we don't have enough electrons at that point in the periodic table. There is no transition metal in that row, but theoretically, those elements can have d orbitals. And when does this normally occur? Well, in molecules having strongly electronegative elements, such as fluorine, oxygen, and chlorine. So if you have a center atom with the atomic number greater than 12, and it's bonded to elements of fluorine, oxygen, chlorine, this is a good candidate for an expanded valence. And expanded valence shells happen when an expanded valence will decrease formal charge on the center atom. So the classic example of an expanded shell would be sulfur hexafluoride. And we draw the Lewis structure like this. If we look at the sulfur in sulfur hexafluoride, it has an atomic number greater than 12, it's 16. It's bonded to strongly electronegative element, which is fluorine, the most electronegative element. And if we look at the formal charge on sulfur, it would be 0. Right? If we calculate the formal charge, it would be 6 minus 0 plus 1/2 of 12. So that would be a total formal charge of 0. So this molecule would be a very, very happy structure. Sulfur has a formal charge of 0. Fluorines all have formal charges of 0. The only issue would be the expanded octet. But as we've seen, this fits the rules to have an expanded octet. It is third period or lower, the atomic number being 16 of sulfur, and it's bound to a most electronegative element, which is fluorine. Let's try another practice of an expanded valence shell. What is the Lewis dot structure of the phosphate ion? And the molecular formula is here. It's phosphorus with 4 oxygens, and the molecule has a total charge of 3 minus. So remember to include those electrons in your structure. And then the second question, does this ion have resonance structures? Our first step would be to calculate the number of valence electrons. So oxygens will have 6, so we have 4 times 6. Phosphorus has 5, so that would give us a total of 29. But we have the minus charge, the -3 charge, so that we have to add 3 electrons for that. So that will give us a total of 32 electrons. Now when we're placing the atoms in the molecule, phosphorus will go in the center. It has a higher bonding capacity. I didn't draw that very well. There we go. Okay. Now we draw single bonds to all the outside atoms, and that uses up 8 of our electrons. So now we're going to have 24 left. So we'll start increasing, filling the octet on the outside atoms. So we use 6 non-bonding pairs for the 4 oxygen. That will use up our 24 electrons. So this would be one possible Lewis structure for phosphate. Now if we look at the formal charges, however, we see that the oxygens will be a -1. I won't go through calculating the formal charges, but you should be able to be comfortable doing that. Oxygen with a single bond, it might be good to remember oxygen with a single bond, 6 non-bonding electrons will give you a formal charge of -1. Oxygen with a double bond will give a formal charge of 0. The phosphorus now, I will calculate formal charge. The formal charge would be 5 valence electrons minus the quantity of 0, no non-bonding, plus 1/2 of 8 bonding electrons. So 5 minus 4 would be a +1. Well, there's that. So again, this structure follows the octet rule. The formal charges are reasonable. They're all 1s. There's no 2s. But can we draw this structure in a different way to minimize the formal charges? And the answer would be yes. If we take a lone pair of electrons from one of the oxygen atoms and form a double bond. Now I'm not going to show all the non-bonding electrons, but that's the structure we'd end up with. Now if we want to calculate formal charges again, the single bond, oxygens with single bonds will be -1. The oxygen with a double bond would be 0. Phosphorus now becomes 0 as well. So the formal charges on this particular structure are better because we have 2 of the atoms at 0. So instead of a -1 formal charge and a +1 formal charge right next to each other, we have 2 zeros. And that would actually be a more correct structure. And to answer the second question, yes, you can have resonance structures. You can move the double bond to any of the 4 oxygens, and it would be an equivalent structure. and that is shown. Oops. Let me erase my markings. That is shown in this resonance structure for the phosphate ion. Okay. Let's try another question. Which of these 4 molecules is an exception to the octet rule? Now take a few minutes and select which molecule is an exception to the octet rule. So if we, the way to solve this would be to draw the Lewis structure for all of these molecules. So NF3, we've seen that before. I'm just going to draw the Lewis structure. Not going to go through all the steps. If you're uncomfortable with drawing any of these, please come see me and we can work through them more closely together. And finally, IF4 plus. Now this one I will go through. Iodine has 7 valence electrons. Fluorine each have 7. So that would give us a total of 35. But we have this plus charge on the molecule, so we have to subtract one of the valence electrons. So we're going to have a total of 34 electrons. Iodine, they both have the same bonding capacity, but iodine is less electronegative, so it will go in the center. Fluorines will go on the outside. We'll draw single bonds. That takes away 8 electrons. We're going to be left with 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we use 24 to fill the octet of fluorine. We're left with 2 more electrons. So they have to go somewhere, so we put them on the center atom. So D will be the correct answer. IF4 plus has an expanded octet on iodine. Now, is this okay? Well, think about iodine. It is it's lower than the 3rd row, and it's bonding to fluorine, which is again a very electronegative element. So that it follows the criteria for expanding an octet. Moving on to section 10.2, and now we're going to start to talk about VSEPR theory, or valence shell electron pair repulsion theory. And here's a kind of a funny way for you to remember what VSEPR theory is, and that's that electron pairs tend to repulse each other, so they spread out to fill the maximum amount of space. We have different ways to depict molecules, and we talked the first part of the lecture about Lewis structures, and those are in 2 dimensions. They show atoms and bonds, but they do not show spatial orientation or 3-dimensional shapes of molecules. And that's where molecular models come in that are actually 3-dimensional. And these show the orientation and the bond angles. And they really help us understand the physicochemical properties of the of the molecule. Now let's see an example of this. We have carbon dioxide and methane. And we see their Lewis structures. Now, if you just take the Lewis structure, you would think that carbon dioxide is linear and methane is a flat molecule shaped like a square, let's say. That's what it looks like in 2 dimensions. Is that accurate? Well, if we look at models for these 2 molecules, carbon dioxide is linear. It's a linear molecule. So the Lewis structure and the molecular model are the same. But methane, however, it's not a planar molecule at all. It's what's known as a tetrahedron. And its bond angles are 109.5, not 90 degrees, as is suggested by the Lewis structure. So what is a bond angle? A bond angle is defined by covalent bonds between 3 adjacent atoms. So here in CO2, we have 3 adjacent atoms, 2 bonds, and this would be the bond angle, which is 180 degrees. In water, the bond angle, again, it's between the hydrogen, oxygen, and hydrogen, and it becomes, because of these lone pairs, which we'll talk about, the bond angle is much less than 180 degrees. It's actually 104.5 degrees. So the molecular geometry is really defined by the lowest energy 3D arrangement of atoms. Both of these molecules have 3 atoms in them, but their molecular geometries are different. And why are they different? It's because of the electron. The electrons in the molecules. And we have a theory to explain this, and it's the valence shell electron pair repulsion theory, but it's easier just to call it VSEPR. So VSEPR theory, it's the geometric arrangement of electron pairs around an atom based on minimizing the repulsion energy. Electrons are negatively charged, they repel each other, so they want to spread out as far as they can to minimize that repulsion. And we have a couple terms. One is the electron pair geometry. Now, this is the spatial arrangement of bonding electron pairs and non-bonding or lone pair electrons. And then the next term to be familiar with is molecular geometry. And this is only influenced by the arrangement of atoms in a molecule. So you only consider bonding pairs, not non-bonding pairs, to calculate the molecular geometry. So what are the steps in predicting a VSEPR structure? The first step is to draw the Lewis structure. And that's why it was important that we went through how to draw Lewis structures. And that's why it's important that you really be comfortable drawing Lewis structures, because to answer any VSEPR question, you're first going to have to draw a Lewis structure. So after we have the Lewis structure drawn, the second step would be to determine the steric number of the central atom. And what is the steric number? Steric number is the number of atoms bonded to the central atom plus the number of lone pairs. So you count bonded atoms plus lone pairs, and that will give you a steric number. Third step, you use this steric number to determine the geometry around the central atom. Fourth step, you find the optimal molecular structure determined by the number of lone pairs and the number of bonding pair electrons. So we have an electron group arrangement versus molecular shape. So the electron group arrangement, also known as electron pair geometry, we brought this term up a couple slides ago. It's defined by both bonding and non-bonding electron groups. The molecular shape, on the other hand, is the three-dimensional arrangement of nuclei of atoms joined by bonding groups. And if we want to determine electron group arrangement or molecular shape, we use a shorthand notation shown here at the bottom, where we have a formula written as AX sub M E sub N. What is A? A represents our center atom. X is any surrounding atom. E is non-bonding pairs around the center atom. And M and N are integers. So M is the number of bonding atoms surrounding the central atom, and N would be the number of non-bonding pairs on the center atom. So let's look at some of these geometries. And this will have center atoms with no lone pairs. So the simplest simplest molecule we can have would have a steric number of 2. Okay, there's 2 atoms bound to the center atom, so the steric number is 2. The formula becomes AX2. That's A is center atom, X because there are 2 atoms bound to the center atom. And the molecular geometry for this molecule would be linear. And we see an example of this would be beryllium fluoride. If we move up steric number to a steric number of 3, now our formula becomes AX3, center atom with 3 atoms surrounding it. And the geometry for this particular molecule, an AX3 molecule, would be trigonal planar. The bonding pairs spread out. They try to spread out to minimize that repulsion, and what you end up with is a molecule that's planar in the form of a triangle, and the bond angles are 120 degrees. Moving on to steric number of 4, AX4 would be the formula, and this is what we call tetrahedral geometry. A very classic example is methane. And in carbon compounds in general, carbon has a bonding capacity of 4. It tends to form tetrahedral molecules. And the molecular angle, the bond angle in a tetrahedral molecule is 109.5 degrees. Moving up to a steric number of 5 now, we have the formula would be AX5, and this is called a trigonal bipyramidal molecular geometry. An example of this would be phosphorus pentachloride. And now you can see that there really are there are different atoms when we talk about the outside atoms that are bound to the center atom. We can have the ones in purple, which we call axial, and the bond angle between an axial and an equatorial atom would be 90 degrees. And then if we look at just the green equatorial, the bond angle between an equatorial and another equatorial atom is 120 degrees, much like the trigonal planar. So this geometry, we have a trigonal planar geometry in the center, but then you have two axial atoms bonded above and below that trigonal planar center. And finally, the steric number of 6. The formula would be AX6, and we call this octahedral geometry. And all the bond angles here are 90 degrees. So it's very important to be comfortable with these molecular geometries, from steric number of 2 to a steric number of 6. And if we look at another figure that depicts this, if you want to think of the bonding atoms to the center atom as balloons, those bonding electron clouds you can think of as balloons. So if you tie two balloons together, where are they going to go to minimize their repulsion? Like, let's say you rub one of the balloons or both of the balloons on your shirt so they get like static charge. And if you ever done that and tried to put two balloons together, they don't really like that. They try to repel each other. So if you think about that, if you think about VSEPR in terms of balloons, it could make it a little bit easier for you to understand these geometries. So if you only had two bonds, two balloons, they're gonna, push each other as far apart as they can, and they would make a linear molecule 180 degrees apart. And you can see the geometries for higher steric number of 3, 4, 5, and 6, all in terms of balloons. Let's try a practice question. So this is for a molecular geometry, and we're not considering any lone pairs. So what are the molecular geometries of BF3 and CH4? Well, we've done the Lewis structure of BF3 before, but let's draw it out again. So remember, boron does not need to have a full octet. It is left of carbon in the periodic table. So this would be the Lewis structure. Now, when we look at boron, what is the steric number? It is bound to 3 fluorines. It doesn't have a lone pair, so it has a steric number of 3. Now, what is the molecular geometry? Well, the molecular geometry would look something like this, where the fluorines are as far apart from one another as they can be. So that would be trigonal planar. Bond angle of 120 degrees. Now what about methane? We've also drawn the Lewis structure of methane previously, and this is what you'd come up with. Steric number now is 4. Carbon is bound to 4 hydrogens, and no lone pairs. So what does this molecule look like? What is the geometry? Well, if we wanted to draw it in 3 dimensions, we would draw something like this. Now, the solid color wedge indicates that hydrogen's coming out of the page, and the dashed wedge indicates that the hydrogen's going into the page. So this would be a rough 3-dimensional approximation of methane. So this is tetrahedral molecular geometry, and the bond angle is about 109.5 degrees. So let's talk about the geometry of central atoms with lone pairs. So up until now, we've really just looked at geometries of molecules without lone pairs. But if we include lone pairs, then the electron pair geometry becomes important. And the electron pair geometry will be one of the 5 geometries that we've presented previously. But the molecular geometry then is going to differ from the electron pair geometry. The molecular geometry is the one that we really care about because this describes the arrangement of atoms present, excluding the lone pairs. And when you talk about the shape of a molecule, that's the molecular geometry is what you're really concerned with. And the bond angles, though, are gonna depend on that electron repulsion, and the lone pair, as we'll see, tends to have a higher repulsive force. So here's another practice question. Now we're looking for molecular geometry. Which molecular geometry is different from electron geometry in these 4 molecules? So which molecule has a molecular geometry that differs from its electron geometry? Again, methane, Lewis structure, CH4. Another way to ask this question would be which molecule has a center atom with non-bonding or lone pair electrons. And we've seen BF3 before. So its Lewis structure would be this. Phosphorus pentachloride. Here's an example of an expanded valence. And finally, the correct answer would be NH3, because it has lone pairs on the center atom. So you could really answer this question just by drawing Lewis structures. But let's also try to answer what the molecular geometry and the electron geometry of each of these molecules is. So we've drawn the Lewis structures for all of them. Next step would be to find the steric number. So for methane, the steric number is 4. So what is the electron geometry? The electron geometry, steric number is 4. They're known lone pairs. So that would be tetrahedral. Also, we can write the formula, the generic formula for methane, which would be AX4. And if you remember, that would give us a tetrahedral geometry. And the molecular geometry is going to be the same, tetrahedral. Let's look at ammonia, NH3. Its steric number now, the generic formula would be AX3E. AX3E1, because there is one lone pair on nitrogen. So now its steric number is also going to be 4, right? 3 atoms bound to it, 1 lone pair. That would be a steric number of 4. What is the electron geometry? Well, the steric number is 4, so the electron geometry is also tetrahedral. Molecular geometry now, this is where it differs. So now we only consider the bonding pairs of electrons, and there are 3 hydrogens bound, but there's that one lone pair that repels the 3 hydrogens. So we're going to get, it's a bad drawing. Let me draw that again. So that would be a 3D representation of this molecule. It's not trigonal planar because we have that lone pair, and that lone pair repulses the other bonding pairs, so they're not planar now. So that would be considered trigonal pyramidal. All right, let's continue on. We know that B is the answer. The molecular geometry is different than the electron geometry. But let's continue on with the other two. BF3 would have a formula of AX3, steric number of 3. The electron and molecular geometries would be trigonal planar. And for phosphorus pentachloride, formula is AX5. The steric number is 5, and both electron geometry and molecular geometry become trigonal pyramidal. So they're trigonal bipyramidal. And let's try to draw that in 3 dimensions so you can see. So we would have 3 chlorines in the plane of our paper, 1 chlorine coming towards us, and another chlorine going into the screen. So that would be a 3-dimensional representation of a trigonal bipyramidal molecule. And it's important to be familiar with the 3-dimensional, being able to express these 3-dimensionally. So we've talked about the electron pair repulsions, but let's go into a little bit more detail. So the greatest repulsion you can have is between a lone pair and another lone pair. Next is a lone pair and a bonding pair. That's the next greatest repulsion. And finally, a bonding pair and a bonding pair will give you the least repulsion. In double bonds, as you might expect, exert more repulsion than a single bond. There's more electrons in a double bond, so there's more negative charge, there's more repulsion. So what happens when you have an atom with lone pairs or double bonds? Well, the bond angles around these central atoms will then decrease as those repulsive forces increase. So let's look at some molecular geometries. Let's look at a steric number of 4. So if we don't have any lone pairs, molecular geometry is going to be tetrahedral. And we see here the formula would be AX4. Now if we add 1 lone pair, that molecular geometry then becomes trigonal pyramidal. Formula is AX3E1. And finally, if we have 2 lone pairs, our molecular geometry becomes bent, and our formula is AX2E2. So let's look at some examples of this. Methane, AX4, tetrahedral molecular geometry, as we've seen. The bond angle is 109.5. Now when we look at ammonia, we've seen this molecule before. It has one lone pair. Its molecular geometry is trigonal pyramid or trigonal pyramidal. And you notice now that the bond angle goes from 109.5 in methane to 107. That's because you have a lone pair of electrons up on nitrogen, which is creating more of a repulsive force. So it's pushing those bonding pairs further down, and it's decreasing the bond angle. Let's look at a molecule that's AX2E2. The good example of that would be water. The molecular geometry is bent, and the bond angle goes all the way down to 104.5. Now, why is that? It's because now we have two lone pairs on the oxygen. So that's even more repulsive force on the two bonding pairs, and that pushes them even further down. So the bond angles decrease as number of lone pairs increases. Let's move on to a steric number of 5. So when we have no lone pairs, molecular geometry is trigonal bipyramidal. When we have one lone pair, the molecular geometry is what we call seesaw. Two lone pairs, we get T-shaped. And finally, if we have three lone pairs, we get all the way back to a simple linear molecule. Let's look at some examples of these. So if we have one lone pair, we have a steric number of 5, but we have one lone pair. Now we get what's known as a seesaw. This would be a three-dimensional representation of that. If you rotate it and then forget about the lone pair for a second, you see that the molecular geometry resembles that of a seesaw. Now if we have two lone pairs now, AX3E2, we see that the molecular geometry becomes something that resembles a T. And I should mention too, we talked about three lone pairs. If you just from the T shape remove one of those atoms, you would remove that one. You would get a linear molecule. And then finally, the steric number of 6, what we call octahedral geometry. When there's one lone pair, we get something called square pyramidal. Second lone pair would be a square planar molecule. And then that's all we're really going to consider with a steric number of 6, only up to 2 lone pairs. And what do those look like? Well, the three-dimensional shape, if we had AX5E1, we would get a square pyramidal molecular geometry shown here. That the lone pair would be an axial, so it maximizes the distance between it and the bonding pairs, and we get what's known as square pyramidal molecular geometry. And if we have AX4E2, we remove the other axial atom, and we're left with square planar molecular geometry. Okay, let's try some practice questions with molecular geometries. what are the molecular geometries for the SCN -1 and NO2 -1 atoms? Okay, our first step is to draw the Lewis structures. So SCN, we have a total of 6 plus 4 plus 5 valence electrons, which would be 15, but we have that minus charge, so we have to add one more, so we have a total of 16 valence electrons. So we arrange the atoms like this. Carbon has the highest bonding capacity, it goes in the center. We've used 4 electrons in bonds, so we have 12 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Octet on carbon isn't filled, so we're going to have to make double bonds. So there's a couple possible choices for this molecule. You can have a triple bond to nitrogen as well. But to choose, we're going to have to think about formal charges. So if we had to choose between these two, we'd really need to look at the formal charges. Nitrogen, in the top case, will have a formal charge of -1, and in the bottom case, the formal charge would be 0. Carbon would be 0 in both molecules. Sulfur is going to be 0 here and -1 here. So really, to choose between these two now, we would need to know the electronegativities of of nitrogen and sulfur. And it turns out that nitrogen is actually more electronegative than sulfur. So the top structure is actually more correct. So that would be the Lewis structure for SCN. Steric number is going to be 2. Formula would be AX2. The electron geometry is going to be the same as the molecular geometry. There's no lone pairs, and that would be a linear molecule. Now let's look at NO2. So we'd have 5 valence electrons from nitrogen, 6 from both oxygens, and 1 from the minus charge. So that gives us a total of 12 plus 5 is 17 plus 1 is 18. Nitrogen, higher bonding capacity, it goes in the center. And now you have, we've used 4, we have 14 more electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Nitrogen doesn't have a full octet though, so we're going to have to make a double bond. Again, it doesn't matter which side we pick, there'd actually be a resonance between the two. So that's the Lewis structure we've come up with. So what is the steric number? The steric number is going to be 3. Nitrogen has 2 atoms bound to it and 1 lone pair. So that formula is AX2E. What's the electron geometry? Well, for a steric number of 3, the electron geometry will be trigonal planar. And finally, what's the molecular geometry? It's a trigonal planar electron geometry, but one of those is a lone pair. So if we draw a shape of the molecular geometry, what we'd get is a bent molecular geometry. Okay, next question. Predict the molecular shape or molecular geometry and the bond angle of sulfur dichloride. Again, the first step, you're going to want to draw Lewis structure. What you'll come up with is this. So the formula of this would be AX2E2. The steric number now is 4. Electron the electron geometry with a steric number of 4 would be tetrahedral. And the molecular geometry, when you have steric number of 4 but 2 lone pairs, what does this become? Well, if you remember, water is a similar molecule. Water has a bent molecular geometry. But let's draw this out. So we'd have sulfur, 2 lone pairs. But remember, those lone pairs have a greater repulsion. So what it's actually going to do is bend those chlorines down. So normally a tetrahedral geometry would have a 109.5 degree angle, but in this case, because the molecule has 2 lone pairs, it's going to be less than 109.5. And it has, if we just look at the molecule, the atoms in the molecule, it has a bent shape, or V-shaped. Okay, on to question 11. Using VSEPR theory, predict the shape of IF4 plus. And remember, this is an example of an expanded valence shell. And if you can look back on, we talked about this molecule previously in question number 6. We drew the Lewis structure. Draw it out again, just real quickly. I'm not going to draw the valence electrons on fluorine, but they're there. So what do we have as far as a formula for this? It would be AX4E. And that would have a steric number of 5. So if you remember a steric number of 5, that gives an electron geometry of trigonal bipyramidal. And now, if we want to talk about molecular geometry, what would that be? Well, let's try to draw this in 3 dimensions. So we have, I'm going to draw the lone pair over here. So we have 1 lone pair on this side, and then we have 2 fluorines on this side, one coming out, one coming into the page. So this would be what is known as a seesaw molecular geometry. If we don't look at the lone pair, and when we're left with just the atoms that are bound, this would be a seesaw shape. Okay, and on to question 12. According to valence shell electron pair repulsion, or VSEPR theory, 4 objects around a central atom will have a tetrahedral arrangement, shown here on the left. And the bond angles are going to be 109.5. Which of the following 3 compounds has a bond angle of 109.5 approximately? So the other way of asking this question would be, which of the following molecules has a molecular geometry of a tetrahedral molecular geometry? So let's look at SF2. The Lewis structure would be this. Again, I'm not showing the fluorine valence electrons. That would be an AX2E2. And if you remember AX2E2, that is a bent molecular geometry. So the angle is going to be less than 109.5. Now let's look at SF3 minus. Just quickly drawing the Lewis structure. Again, not showing valence electrons on fluorine. That would give us a formula of AX3E2. And this is actually a T-shaped molecular geometry. And the angles on this would be, right around 90 degrees, probably a little bit less than 90 because of the 2 lone pairs. Finally, SF4, Lewis structure shown here. Formula would be AX4, and you notice there are no lone pairs, so the electron geometry is going to equal molecular geometry. In this case, it'd be tetrahedral. And tetrahedral have bond angles of 109.5 degrees. So the answer here would be C. Right. Moving on to section 10.3. In this section, we talk about bond polarity. Now, we talked about polar covalent bonds in the 3rd lecture. And I just want to bring this scale of electronegativity back up again. Again, this was developed by Linus Pauling. He actually won the Nobel Prize in 1954 for his work in chemical bonding and electronegativity. So what is required for a polar molecule? Well, first and foremost, the molecule must contain polar bonds. And if you think back to the last lecture, a bond between atoms with a difference of electronegativity of greater than 0.4 would give you a polar bond. There's another requirement, though. It's not enough to have polar bonds. You also have to have them in an orientation that results in a net charge separation from one part of the molecule to another. So what does that mean? If we look at carbon dioxide, CO2, it has polar bonds, but they're linear. This is a linear molecule, and they're equal and opposite direction, so they end up canceling each other out. So this molecule is nonpolar. So let's look at some other examples. If we look at methane again has polar bonds. but they all are facing in towards carbon, and it's a symmetric molecule, so they cancel each other out. So this molecule is nonpolar. Water. Now we have polar bonds, but because of the lone pairs, now this molecule is not symmetric, and we get a net dipole. Another way you can think of this is if you add both of these dipoles together, you'd have one going that direction, another going this direction, and then your net dipole now becomes in this direction. And that is shown here. So this molecule has a dipole, and it's a polar molecule. So as we talked about last time, there's what's known as a bond dipole, shown as these arrows, and that indicates a separation of charge within a bond. But for the molecule to be polar, the sum of these dipole vectors has to be greater than 0. Now, measuring polarity, this is just for your information. We have what's called a dipole moment, given by the Greek letter nu, and if you're interested in how that's actually calculated, your book gives you a figure, but we're not really going to be talking in detail about it in this class. So if we look at some permanent dipole moments of some polar molecules, you see that HF, it's a very polar molecule because you have fluorine's the most electronegative element. And then you see some other polar molecules, and decreasing down to carbon Cl3F. So all 4 of those bonds again are polar, but the fluorine's just a little bit more electronegative than chlorine, so you get a slight net dipole in that direction of the molecule. And it really, this is this table in your book is really a good practice. If you can look at these molecules and understand that they are polar and there is a net dipole, you'd be in good shape. So if we look at just a net dipole for the molecule, HF, I mean, that's easy to see. What about water? You have 2 dipoles. If we add them together, we'd get a net dipole going up through the center of the oxygen atom. And that's the same with nitrogen. We have 3 nitrogen-hydrogen bonds. And remember, this molecule is not planar, it's trigonal pyramidal. So you're actually going to get a net dipole up through the center of the nitrogen. If we look at CHCl3, the chlorines will give you a slight dipole towards the bottom of this molecule. And the hydrogen-carbon bond is also pointing that direction, the dipole. So your net dipole would be going down through the center of the carbon. All right, final practice question for the lecture. Select the polar molecule. All right, let's draw some Lewis structures. BF3 we've seen many times before. Its molecular geometry is trigonal planar. These are all polar bonds, but this is a symmetric molecule. They're all 3 of the bonds are in the same plane, so they cancel each other out. Now, if we look at X xenon difluoride, And this is an example of an expanded valence. So let's draw this Lewis structure together. Xenon has 8 valence electrons, fluorine has 7 each. So that would be 22 total valence electrons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 for the bonds, 17, 18, 19, 20, 21, 22. So xenon actually has 3 lone pairs around it. Formula would be AX2E3. Steric number is 5. So the electron geometry would be trigonal bipyramidal, but the molecular geometry here is linear. And again, these are polar bonds, but it's a linear molecule, and they're equal in strength and opposite in direction, so that is nonpolar. There's no net dipole. And the same is going to be true for carbon disulfide. Now in this case, carbon and sulfur actually have very similar electronegativities, so these bonds themselves aren't even polar. But even if they were, it's a linear molecule. Finally, by the process of elimination, we can consider bromine trifluoride is going to be the answer. But let's look. So here's our Lewis structure. Now what formula is this? It's AX3E2. Steric number is 5. The geometry now becomes, when you have a AX3E2, that molecular geometry is what's known as T-shaped. And are these bonds polar? Well, fluorine is more electronegative than bromine. So we see that the first two, these upper bonds, would cancel each other out. But we have another bromine-fluorine bond down here, and then thus that becomes, there's no canceling bond on the other side of the molecule, so that would become the net dipole for this molecule. So this is a polar molecule. All right, that's the end of Lecture 4. In Lecture 5, we're going to be covering material from Chapter 11, and that covers valence bond and molecular orbital theories.